Hello everyone. In this video we're going to learn about an important group of mathematical expressions called polynomials, and we're also going to learn how to combine polynomials. When we say polynomial, we're referring to an expression which has terms, and each of those terms have to look like this expression right here. So we have a constant a, which can be any real number. This notation here means a belongs to the set of real numbers. So the coefficient is the name for that number, and it can be any real number times some power of a variable. Now, that exponent which creates this power is going to have a very specific form. It has to be a whole number. If you recall, the set of whole numbers is the set which starts with 0 and then goes on to 1, 2, 3, etc. So each term of this mathematical expression, which we call a polynomial, has to have this form. This is, of course, a simple polynomial in just one variable. So we say that we have a polynomial in x, meaning in the variable x. Now, for each of these terms, as I just mentioned, the number here, this is just a constant which is being multiplied by this variable power. The constant is called the coefficient of the term, and the exponent of the power we call the degree of the term. Now, the x to the n part, because x is the variable, is known as the variable part of this whole term, ax to the n. Now, of course, a polynomial is going to have usually more than one term. Not always, but usually. So what do we call a degree of a polynomial? Well, it's not going to be the sum of all the degrees or anything like that. What you do is you look for the term in the polynomial that has the highest degree, and then you take that as the degree for the entire polynomial as well. We're going to see all of this in an example in a minute, so just wanted to get some of the terminology out of the way. Now, if a polynomial does indeed just have one term, we call it a monomial. If it has two terms, we call it a binomial. And if it has three terms, we call it a trinomial. If it has more than three terms, we don't have special names for it. We'll just say a polynomial with 5 terms, a polynomial with 10 terms, etc. So no special names for those polynomials that have more than 3 terms. To get a better feel for it, let's look at some examples. Like here in this first example, notice we have 5x cubed plus 3x squared minus 9x plus 17. So here we have a polynomial that has obviously 4 terms. So the only term that you may wonder how it fits the definition, because remember we said each of the terms has to have the form ax to the n, where the coefficient a is a real number and the exponent n is a whole number. Now, that's not hard to see for how each of these 3 terms satisfies that requirement, because of course 5, 3, and -9 are real numbers, and 3, 2, and of course the exponent here when we write nothing is a 1. So that's also fine because all 3 of those are whole numbers. So what about the 17? Well, as it turns out, if you recall from previous discussions, x to the power of 0 is 1. So we can take 17 and we can write it as 17x to the 0. So that also satisfies the requirement for the way that each term of the polynomial is supposed to look like. And here we have another one. So notice the coefficients are a bit more complex, but nevertheless, they are just real numbers. And here, the last term, negative pi, remember pi is a constant. Its value is approximately 3.14, so negative pi is approximately negative 3.14. And remember, again, this satisfies as the form ax to the n, because we can always write negative pi as negative pi. Guess it before you look. I hope you guess y to the 0, because that's exactly what it is. All right, so we can write it as negative pi y to the 0, and so therefore that satisfies as well. So here again, now this one, the one that we just looked at, has 3 terms. This would qualify as a trinomial. This one has 2 terms. This would be a binomial. And notice that the degree of this term is 6. The degree of this term is 1. Remember, there's always that invisible 1 as the exponent. So we say the degree of this entire polynomial is 6, because that's the degree of the highest degree term. For this polynomial up here, the degree would be 3, because the highest degree term is a 3rd degree term. So now this term here has a degree of 2, this one has a degree of 1, and this one has a degree of 0. So a constant is also known as a 0 degree term. And here again, here we just have a simple monomial, because there's only one term and it's just the number 7. So does it satisfy? Of course, I think you know by now. We can write it as 7 times any variable you like to the power of 0. So we'll just go with x. So this is in fact a polynomial with one term, so it's a monomial, and its degree would be 0. All right, so on this side we have a few examples that would not qualify as polynomials. So for example, right here, it looks kind of polynomial-ish, you could say, but the problem, of course, I'll let you think about the problem before I tell you. See if you can figure out what's wrong with this polynomial. This expression which deprives it from the opportunity of being called a polynomial. And I think you have guessed it, it's the first term which is the problem, because yes, the coefficient is fine, that's a real number, but the exponent here is not a whole number. Remember the set of whole numbers? They start with 0, etc. So -2 is considered an integer, but not a whole number. So here we state the fact, why is this not a polynomial? We can just say -2 does not belong to the set of whole numbers. All right, so here we have another expression which is not a polynomial for a very similar reason. Again, because the exponent on this first term is not a whole number, and we know what the whole numbers look like. So again, here we can say the reason this is not a polynomial is because of the fact that square root of 2 does not belong to the set of whole numbers either. All right, so in this next one, this does not qualify as a polynomial because there's no way we can go ahead and have this power move to the top and this exponent remain positive. So very soon we're going to learn that this actually can be brought up, but it turns into 3t to the -3 minus 2t squared minus 5t. So again, here we're unable to satisfy the general form of a term of a polynomial. So for the same reason as the previous one, so we can say 3 over t cubed is the same as 3t to the negative 3, and negative 3 does not belong to the set of whole numbers. All right, so in our last example, this looks very much kind of like a polynomial, except, even 2.1 isn't going to cut it. It's close to a whole number, but not quite. So why is this not a polynomial? Because 2.1 does not belong to the set of whole numbers. All right. So make sure you understand the basic meaning of a polynomial, the definition of a polynomial before we proceed. At any point in the video, definitely pause and reflect. Also, treat what's going on here like a classroom. Take notes, have paper and pencil handy, be working through these problems with me. That's the best way to learn. You're not going to learn mathematics by just watching a video. It doesn't work out like that. So make sure you're actively engaged. That's called active learning rather than just passively watching a video. That's not going to be enough to really solidify the material for you. All right, so here we're going to look at some polynomials, and we're going to kind of break them down into the different terms that are contained in the polynomial. First of all, we notice this first one. We've seen this before, so we're just looking at them a little bit more closely now. So we notice that there are 4 terms. Is there a special name for that? No, we don't have a special name for 4 terms. Now, which one is the highest degree term? It's this one. So it's the 5x cubed. Now, notice the coefficient of that term is 5. The variable part is x cubed, and the degree is the exponent, which is 3. So what is the degree of the whole polynomial? Well, remember, the degree of a polynomial is the same as the degree of one of its terms that has the highest degree. So, and that happens to be 5x cubed. So the degree of the entire polynomial is also 3. Not only is 3 the degree of this term of the polynomial, but it's also the degree of the whole polynomial as well. In this next one, we have 3 terms. We do have a special name for that one. It's a trinomial. Let's zoom in on the term with the highest degree. It's this one. And we know that the coefficient is going to be the negative square root of 5. The variable part is the y squared, and the degree is 2. So that also makes the degree of the entire polynomial 2 as well. This next one is a binomial because it has 2 terms, and that's the term with the highest degree. It has a coefficient of 12, variable part u to the 6, degree 6. So 6 is also the degree of this whole polynomial. And the last one is a monomial. Remember, we can write 7 as 7x to the 0. So therefore, the degree is 0. And that means the degree of the entire polynomial, which is just that simple 7 anyway, is also 0. So make sure you understand what each of these different components are before we proceed. Now, sometimes polynomials can have more than one variable in them. As long as each of the variable powers has a whole number exponent, we should be good to go, no problem. And these coefficients, of course, need to be real numbers. And we can see that, for example, this trinomial satisfies that. So this would be a trinomial not just in x, but in x and y. Okay, so this is a multivariable polynomial. And to find the degree of each term, Like, let's focus on this first term, right? 3x squared y cubed. To find the degree of that term, we add those exponents, okay? So the degree of this term would be 2 plus 3, which is 5. So the degree of this term, 5xy, remember there are two invisible ones that I have highlighted here. And so the degree of this term would be 1 plus 1, which is 2. And the degree of the term 7, remember you can write 7 as 7x to the 0, or just as well we could have written it as 7y to the 0, or we could have even written 7x to the 0, y to the 0 if we wanted to. We could do that too. And in either case, even if we wrote it as 7 x to the 0, y to the 0, the degree would still be 0. Notice, because what's 0 plus 0? It's still 0. Here, of course, I meant still. All right. And what is the degree of the whole trinomial? Well, which one of the terms had the highest degree? Notice it was that first one. So we get the degree is 5. Let's quickly go back to the previous screen. Notice something in these examples we had, which were all in one variable. Notice they're all written from the highest degree term going down to the lowest degree term. When this happens, we say this is a polynomial written in descending order of powers, because descending meaning going down, right? The degree of this term is 3, this one is 2, this one the degree is 1, and this one we know is the degree is 0, because we can multiply it times x to the 0. So this kind of every single one of these actually is a polynomial in descending order of powers. Of course, for this one it's moot, given that there's only one term. Often when we want to give a final answer for a problem involving polynomials, we like to write the answer in descending order of powers. When two variables are involved, writing it in descending or ascending order is not as simple. So what you can do is you can pick one of the variables and, for example, write it in descending terms of descending powers of that one variable. But oftentimes when one variable descends, the other ascends. So we don't really worry about descending order when we deal with more than one variable. Now, a very important topic when it comes to polynomials is the notion of like terms. And of course, when we have terms like these two, what we consider to be like terms are terms that have equal variable parts. Here we say in simplified form. The reason for that will become obvious in a minute. So notice that here, of course, remember the coefficient is 2 for this term, 3 for this term. The degree on both of them is 2. Remember, in order to be able to combine like terms in the very near future, we need the variable parts to be the same. And here they are exactly the same. And that's why these two terms would be considered to be like terms. Notice that here they look a little bit different. That's why we said in simplified form, because on the surface of things they look different. But if you know your exponents, you know that this second term can be written as 2/3 u to the 4. So now we can see that indeed they are like terms. Remember, we don't care about the coefficients being equal. They may be, they may not be. It doesn't matter at all when it comes to determining whether two terms are like terms or not. What we need is for the entire variable parts, including the base and the exponent, to be equal once both have been written in simplest form. Notice here again, pi is the coefficient here, square root of 3 there. they're not simple whole number coefficients, but that doesn't matter, because what matters is that the variable parts, which are x squared, are the same. On this side here, we have some examples of unlike terms, terms that are not alike. In this first example, notice that the coefficients are the same, but we don't care about that. What we're really concerned with is the entire variable part. So the entire variable part here is x squared, and here it's x cubed. And of course, x squared and x cubed are not the same thing. So they're not equal. So therefore, these two would not be considered like terms. Here, notice that the exponents are the same. These we don't really care about whether they're equal or not, but the difference is that the bases aren't the same. So that makes the powers not being the same. So therefore, these would not qualify as like terms either. Same here. Again, we have the same coefficient, but these are just two constants, and that doesn't matter. It's the variable part that matters, and those are different. So here's some examples of unlike terms. So the question is, why are like terms important? Well, because when we have like terms, we can combine them. It's like saying 2 apples and 3 apples. You can combine them to get what? 5 apples. Of course, if we have 2 apples and 3 oranges, we can't say we have 5 of either one. We can't combine them like that. All we can do is say, okay, we have 5 pieces of fruit, but we can't combine them nicely like we can if they're both groups are apples. So here, in the same manner, we have 2x squared and we have 3x squared. So you have a total of 5x squareds, right? So the rule that allows us to combine like terms is the right distributive property used in reverse. So notice that the right distributive property, it basically just says you can distribute from the right, or you actually need to. So if we have an expression like this in parentheses with a number written here, we know that that number gets distributed by both of those. So we get b plus c times a equals ab plus ac. Now we're going to use this rule in reverse. This happens in mathematics quite often. You learn something in one direction and then you apply it later going the other way. So notice that here, just as you know that if you see this, you can easily get to this, now you have to become just as comfortable as with seeing this and then being able to write it like this. So basically, if we have AB plus AC, we can write that common factor A out here, and then just write what's left, B plus C in the group. So this is actually the process that's going to be required to combine two like terms, because when we have 2x squared plus 3x squared, x squared is going to play the role of this common term like A. So we can write it on the outside here like we did with the A, and then we can just combine the coefficients, 2 plus 3. So we end up with 5x squared. Now, do we often show this step? No. We usually just jump from here to here. But nevertheless, it's important to know why things work the way they do. This is how you start gaining some depth when it comes to mathematics and just logical understanding in general. Okay, so oftentimes we take things for granted, but it's important to understand those little rules, because that's how you really become a good mathematician. All right. Now, even though in the simple case of like 2x squared plus 3x squared, we may not show that step, when it gets more complex like this, it's highly recommended that you do show this intermediate step. So here, for example, we can see these three are like terms, and the variable part that's common to all of them is x squared. So we can write that here, and we can just go ahead and combine the coefficients. So we have 1/2 minus 2/3 plus 1/4. And now we're just going to combine these three fractions with a common denominator of 12. So that means, for example, the 2 we need to multiply by 6, which means, of course, we have to do exactly the same on the top. The 3 here needs to be multiplied by 4 to get us the 12. And of course, we have to do the same to the 2. Anytime we multiply a denominator of a fraction by a number, we have to do the same to the numerator to keep the value the same. Because then we're just multiplying by, like, for example, 6/6, which is 1. So we're not changing the number, we're just changing the way it looks, because 1/2 is exactly the same as 6/12. They're both basically 0.5, right? So same thing here. So, and also the 4 we need to multiply by 3. So we have to do the same to the 1 on the top. That's where we get the 6 minus 2 times 4, which is 8, plus 1 times 3, which is 3 over 12, and then x squared on the side. So now we just combine these. 6 minus 8 is -2 plus 3 is 1. So we get 1/12 x squared. So again, when the coefficients are a little bit more complicated, definitely show the intermediate step so you don't make any careless errors. So here we have another example. See? So here we're just going to write the y cube, and we're going to combine these more complicated coefficients. So we're going to get pi minus square root of 2 plus the cube root of 4, like that, times y cube. And these, of course, are not alike as numbers, so we can't combine them. So we just leave it like this, and this is considered to be the combined form of these three terms. Now that we've learned how to combine like terms, we can proceed and go ahead and combine polynomials. So here we have an example of two trinomials that we are going to be combining. So the first thing that we're going to do when we tackle a problem like this is we're going to get rid of the parentheses that are available, of course, by carefully seeing whether we can just drop them or whether we need to do something before we drop them. So, of course, in this case, notice these pair of parentheses, they're just placeholders for this polynomial. They're just containers of this polynomial. They're not performing any kind of a multiplication action or anything like that. So those can be safely dropped. And here, because that's a plus and no number written here, so you can imagine an invisible 1. So that's just like saying plus 1 times all of that, which of course, multiplying a 1 into a polynomial isn't going to change anything. So we can safely drop those parentheses as well. So basically, we're going to have, let me go ahead and go back to the other color. It's a little easier on the eye. So 2x squared plus 3x minus 5. I just dropped the first set of parentheses. And so now I can just keep going horizontally like this. So here I know positive times negative is negative. So my next term will be -3x squared. The next one will be -7x, and then plus 18. Or I can even be more clever, and I can go ahead and write the -3x squared right down here to go ahead and put it close to the term that it is like that. So the next term will be -7x. So I'll go ahead and write that under the 3x. And then we have plus 18, which we can just go ahead and write like that. So now we can just draw a line and just combine. See how easy that is? So 2x squared minus 3x squared, that's going to be -x squared. 3 minus 7, that gives us -4x. And -5 plus 18, that gives us +13. And right there, we have combined those two polynomials. Combining polynomials is a general term which means either adding or subtracting. So it includes both addition and subtraction within itself, the term combining. All right, so simple, just have to be careful not to make any careless errors, and we should be good to go. With all the problems that we do, you should pause the video, see if you can do it on your own, and then continue just to verify whether you did it correctly or not. That is how you learn mathematics, by doing it, okay? Not just by watching it, remember that. All right, so here we're going to subtract polynomials. And subtraction always requires a little bit more care than addition, because we have a situation here where we're going to need to distribute this negative out here. First, you can imagine there being a 1, invisible 1, so you're going to distribute -1 into the second parenthesis. So the first pair of parentheses, they can be dropped safely. So we can just rewrite it as 2x squared plus 3x minus 5. Now I'm going to go ahead and start to distribute the -1. So I get negative times negative is positive 3x squared. Again, I could keep going horizontally, or better yet, I will group them from the get-go. So 3x squared, and then negative times negative gives me positive 7x. So I can put that here. And negative times positive gives us negative 18. Now we just combine those. So 2 and 3 gives us 5x squared. Remember, the subtraction has already been handled, so now we're just combining these. So 3 and 7 gives us 10, so plus 10x. -5 and -18 give us -23. So there we have handled the subtraction, as well as we have combined the like terms to simplify the final result. All right, so as our last example for this video, notice that we're saying subtract this polynomial from that polynomial. So the way you don't let something like this confuse you is you first think of a simple example for yourself. So for example, suppose I had asked you to subtract, let's put it down here. Let's say you wanted to subtract 3 from 5, right? If I asked you to do that, I think you wouldn't have any problem realizing that you would have to write the 5 first and then go -3. See, now you're subtracting 3 from 5, right? So if you want to generalize it a little bit, I could say to you, subtract A from B, right? So which one would you write first? Think about it. Okay, I think I heard you say B, right? You're right. All right, so we would write B minus A, correct? So now remember, now you can think of this whole polynomial here as A. We're going to subtract it from B, right? So remember which one we need to write first? The B. So we're going to write 5/2 y cubed plus 1/3 y squared minus 3/4 y minus 11/5. And we're going to subtract from that. Now remember, I don't really need parentheses around that first polynomial, but I do need it around the second one because I'm subtracting. So minus, now I'm going to write that other polynomial, the A. So 1/2 y cubed minus 2/3 y squared plus 1/4 y minus 1/5. All right, so Once again, we can go ahead and just write the first polynomial, 5/2 y cubed plus 1/3 y squared. I do hope that you have paused and tried this on your own and are just now watching to make sure we have the same answer, right? See, I knew it. All right. So now we're going to go ahead and distribute the negative, remember, invisible 1. That's like saying distribute -1 into this. Remember what distributing -1 is going to do. It's going to change all the signs, right? So we get -1/2 y cubed plus 2/3 y squared minus 1/4 y, and then plus 1/5. All right. So now we're just going to combine. So 5/2 minus 1/2. That's easy because they have the same denominator. So that's just going to be 5 minus 1, which is 4/2, which is 2. Let me go ahead and just write 4/2 first. So we get 4/2 y cubed. For the next two, we have 1/3 plus 2/3. Again, easy because they have the same denominator. So we get 1 plus 2, which is 3/3. So we get plus 3/3 y squared. Again, like fractions here. So we get -3 minus 1, which is -4/4y. Two more like terms here. So -11 plus 1, which is -10/5. Now, we just simplify now. We know that 2 and 4 are going to leave us 2. These two cancel out, just leave us 1. Same here. Of course, they'll leave us -1 there. And these two leave us 2. So now we're just going to clean it up.